Now, in the last part of this lecture, we got a good look at intermolecular forces at play and how greater intermolecular forces result in higher boiling points because it takes more energy to disrupt them than weaker intermolecular forces. In this part of the lecture, we're going to take a deeper dive into looking at these forces at work in the condensed states, which means liquids and solids. And we're going to start off by talking about surface tension, and we're going to find surface tension in liquids. And this results from the intermolecular forces of liquids having a tendency to minimize the surface area. So basically what this means is that liquids, because of the strong intermolecular forces that are holding them in the state, they have a tendency to form a sphere. But on the planet Earth, they can't because they also have to contend with gravity. So instead what ends up happening is that liquids have a tendency to mound up instead of forming a complete sphere. So the surface tension of a liquid then is the energy required to increase the surface area of a given amount. So what this means is that here we are in chemistry, and we try to correlate these things to something we can measure, and we can measure the amount of energy that it requires to disrupt this natural tendency of fluids to mound up. And that's what we define surface tension as. It's this energy required to disrupt the system that naturally occurs in liquids. So if we were to look at water and benzene, we have water, which is a very polar molecule, versus benzene, which is a hydrocarbon, and hydrocarbons are nonpolar. So the surface tension at room temperature of water comes in at 72.8 millijoules per meters squared. And for benzene, it comes in considerably less at 28 millijoules per meter squared. Because remember, this is the surface area, and we're measuring the surface area here in meters squared. So this tells us about the energy needed to disrupt water versus benzene, and we can see that because water has polarity, it has stronger intermolecular forces, it takes more energy to disrupt it than it would for benzene, which is a hydrocarbon, and the only intermolecular forces at work here are those fleeting dispersion forces. So what we just saw on the previous slide was that the stronger the intermolecular force, the higher the surface tension. But we also made a note that at room temperature, so temperature comes into play here as well. So what could we say about temperature? Well, we could say that raising the temperature of a liquid is going to reduce its surface tension. And if you've ever watched water boil, you can see that that is the truth. So raising the temperature of a liquid is going to increase the average kinetic energy of the molecules, and this increased molecular motion is going to make it easier to disrupt those intermolecular forces and stretch out that surface area. So this is why raising the temperature is going to reduce surface tension. Now, the layer of molecules on the surface of a liquid actually behave differently than the ones on the interior of the liquid. So the surface molecules are having a different experience than the interior molecules. And the reason why is because of the cohesive forces at play on the surface molecules. And cohesive is the ability of a substance to adhere to itself. Adhesion is the ability of a substance to stick to something other than itself. So surface tension, the molecules at the surface of a liquid have to contend with cohesive forces because they're going to have a net pull into the interior of the liquid. So the surface layer of a liquid is going to act kind of like an elastic skin. So it's going to be the one that will round and flatten depending upon the forces at work at it. And this is what's going to allow something to float on the surface, even though it is a solid and would be considerably denser than water. So if the forces are just right, certain things can actually float on a liquid even though the density might be greater. And so here's a great example right here, this water, this paperclip floating on some water. Now, another characteristic of liquids that we can use to measure and quantify them is something called viscosity. So what is viscosity? Well, viscosity is the resistance to flow. So liquids have a tendency to flow because remember they will assume the shape of a container if there is one, and so what allows them to do that is flow. And there is a unit associated with viscosity, and it is the poise, and it is a contrived unit. It has other associated units with it, which is grams per centimeter seconds. Now we don't say poise, even though that's what this looks like, because poise is named after the Frenchman who discovered this quality and came up with this unit. And his name was Poiseuille. So thankfully it got shortened to poise, and that's all we need to know is the poise. So the poise is often given in centipoise, and the units, like for water, 1 centipoise, has 1 centipoise of viscosity at room temperature. And here's a lovely chart that's giving you some other viscosity measurements of some hydrocarbons. So as we just saw on the previous slide, the stronger the intermolecular attractive forces, the higher the liquid's viscosity, the more resistance to flow that it has, because those intermolecular forces are going to hold it together. Now, the more spherical the molecules in that liquid are, the lower the viscosity. Now, if we think back, we talked about how different shapes of molecules are going to have different surface-to-surface contact, and we used the examples of pentane. So here we have pentane where all the carbons are in a line, and we said that this one is going to have greater surface-to-surface contact than the pentane that's more or less spherical or round in its molecular shape. And this has to do with the, again, the amount of intermolecular forces. Now, the only thing at work in a hydrocarbon is going to be dispersion forces, but there are greater dispersion forces occurring along a straight chain of carbon than there is in a ball of carbon. And the other thing that can happen here is that these round molecules can actually roll more easily. Now, we know that changing the temperature of a liquid is going to change the viscosity, and if we look here on the chart, what we can see is that we have water at room temperature, about 20 degrees Celsius, and as we stated previously, it comes in at a viscosity of 1 centipoise. But if we bring it up to boiling, which is 100 degrees Celsius, then we can see that the viscosity then goes to 0.1282. So from this, we can see that raising the temperature of a liquid is going to not only increase its kinetic energy at the molecular level, but this increased intermolecular motion is what's going to make it easier to overcome the intermolecular attractions and cause that substance to flow. Now, I don't know if you've ever noticed this, but you can tell the difference between ice cold water and water that's boiling. One has a greater sloshiness than the other one. And if you've never done that, I'd be surprised if you haven't, but if you've never done that, actually go to your kitchen at some point and put some water in the freezer, and just before it freezes, look at it versus something that you've just boiled and look at it. There is a visible difference between those two waters at different temperatures, and it's actually visible. And what you're seeing is the effect of temperature on the viscosity of water. Now, another interesting thing we can observe in fluids is something called capillary actions. So what is this? Well, this is the ability of a liquid to flow up a thin tube against the influence of gravity. Seems kind of counterintuitive. So what is happening here is that the liquid is rising in the tube until gravity actually overcomes the forces that are at play. And interestingly, as we see in this picture, the narrower the tube, the higher the liquid will rise. So what is happening here that allows this to occur? Well, it's the result of two forces working together. One is called cohesion and the other one is called adhesion. So what are these? Actually, I mentioned these a little bit ago. Adhesive forces are going to be what holds the liquid together. And the adhesive forces are the forces that allow the liquid to stick to the walls of its container. So the combination of these two things is what allows this liquid to creep up along the sides of the tube until it reaches a point where it's so spread out, the forces are diminished, and then gravity comes in and it stops it. Now, along the same lines as capillary action, but not nearly as dramatic, is something that forms on liquids called a meniscus. And we see two different sorts of meniscuses, menisci, I'm not for sure what the plural is here. So the meniscus is the curving of the liquid surface in a thin tube, and it's going to be due to the competition that we have in between the adhesion, which is the ability of the liquid to stick to the tube, and the cohesion, which is the ability of the liquid to stick to itself. Now, the two substances that we're looking here is water on the left and mercury on the right. And we'll notice that the meniscus of water is kind of a dippy downy sort of a shape, and the meniscus of mercury is kind of a pokey uppy sort of a shape. All very technical terms there. So what do you think is explaining the difference here? Well, when we think about what's at work to create the meniscus, it's the interplay between cohesion and adhesion. So we might conclude by looking at these two that the water has a stronger adhesion to the glass than to itself. So we could say that water's adhesion to glass is stronger than its cohesion to itself, and as a result it's rendering this concave meniscus. So from this we could then conclude that just the opposite is true for mercury, that mercury has this convex shape because mercury is more attractive to itself than it is to those glass walls. And something that we haven't talked about in this chapter yet, but that is metallic bonds. You might remember that metallic bonds are bonds that exist among metals, and they're stronger than intermolecular attractions. So when we might think of metals, we might be thinking of things that can develop charge, but remember, if you put a metal together as just a pure metal, what ends up happening with all of those electrons that it casts off is that they end up kind of floating around, and that ends up being what's called a molecular metallic bond, and that is an exceptionally strong bond. It's obviously stronger than intermolecular attractions, which is why mercury sticks to itself. Now, another parlor trick that liquids can do is something called vaporization. And here we're going to revisit the idea that the molecules at the surface of a liquid are having a different experience than the ones that are deeper down in the liquid. Now, it is possible that at the surface of the liquid, a molecule could get enough energy, even though this substance is not at boiling point, that this molecule could get enough energy that it could launch itself free of the liquid, that it could have enough energy that it gets to overcome the attractive forces of cohesion. And as a result of this, our liquid will then move into vapor state. So we commonly say it evaporates, but actually what it's doing is vaporizing. Evaporation is when you bring a liquid to its boiling point and then you initiate that state change. Vaporization is what we see happening when you set a glass of water out on the counter and then don't touch it for a week. Eventually some of that water, if not all of it, is going to be gone because it has turned into its gaseous phase. Now, if you've also noticed, the larger the surface area of the liquid, the faster the rate of evaporation, and that's because there's more opportunity for more of those molecules to break free. So having this larger surface area is going to help these molecules escape and become what we call a vapor. So what's the difference between water that has become gaseous as a result of vapor and water that has become gaseous as a result of boiling it? Nothing. It's still the same water molecules that have undergone a phase change. Just one takes longer. Now, as we talked about the glass of water, if you put it on the counter, there's only going to be a small fraction of the molecules at the surface that are going to gain enough energy to escape the intermolecular forces at work in a glass of water. However, if you were to put a little bit of energy into that system, that is, heat it up, because heat is the currency of the universe, if you were to put some heat into it, increase the temperature, then the fraction of molecules with the ability to escape suddenly increases. So then we can conclude that the higher the temperature of our liquid, the faster the rate of evaporization occurs, which should make sense. So let's summarize what we know about vaporization. Well, we know that the rate of vaporization increases with an increasing temperature. So at a temperature below zero, we would have a low vaporization, but if we were to add some energy into that system and increase the temperature, then we would have high vaporization. The other thing we can conclude is that the rate of vaporization will increase with increasing surface area. Here I have a couple of wine glasses. Now, it's not wine that we're worried about vaporizing. There's a couple of other chemical reactions or phase state changes that can occur depending upon what you put in that glass. Yeah, actually it's interesting science behind it. So you have a large mouth wine glass because what you want to have happen is you want to expose the wine to air molecules, so there'll be some oxidation, and that actually enhances the flavor. The wine glass on the right is a champagne flute, and we want to hang on to the bubbles in champagne, which is one of the reasons why we keep that one with a small surface area. So wine glasses are a perfect example of using surface area to engage different chemical reactions. And the third thing is that the rate of vaporization is going to increase with decreasing strength of intermolecular forces. So if you've got strong intermolecular forces, then you're going to have a lowered rate of vaporization. If you have weak intermolecular forces, you're going to have an increased rate of vaporization. So let's look at the energetics of vaporization. Let's see what sort of energy exchange is happening in this sort of a system. So when the high energy molecules are lost from the liquid, then what happens is that the average kinetic energy is lowered. So it is like the liquid has also lost some of its energy. And if energy is not put back into the liquid, because this liquid has now lost some of its energy, the temperature is going to decrease. So what we can conclude from this is the following. So vaporization is an endothermic process. So let's look at that. So in this sort of scenario where we have our container of water, we're looking at vaporization as an endothermic process, we're concerned with what's happening with the water, because the water is going to undergo some sort of a transition, a phase change. And in order for that to happen, that means that water molecules at the surface have to have some energy available in order for them to become liberated. And it is this input of energy that makes vaporization endothermic. Now, the opposite of vaporization is condensation. And this is an exothermic process. And in this scenario, what we're talking about is what's happening outside of the liquid with the molecules that have just become vaporized. So we're looking at the water vapor that has just formed. And this is considered an exothermic reaction. Condensation is considered an exothermic reaction. So what has to happen here is that these vaporized water molecules have to lose energy in order to go back into liquid. So when water becomes liberated from its liquid state, it's called vaporization, it's endothermic, and when water condenses, it's releasing energy, it's lowering its energetic state, which makes it an exothermic process, and this is what we call condensation. So as we just stated, vaporization requires the input of energy to overcome the attraction between the molecules that we find at the surface of our liquid. So why does condensation happen? Well, some of these newly vaporized molecules are going to lose energy through molecular collisions, most likely. And the result of that is that some of these molecules are going to get captured back into the liquid when they collide with that. Because remember, these guys haven't moved too far away from the surface of the liquid from where they just left. And once their energy gets lowered enough, then the energy of that individual molecule cannot overcome the intermolecular forces at play in the water or the liquid. And also some may just stick and gather together to form droplets of liquid, particularly on surrounding surfaces. And we've all had that experience when you're drinking a cold beverage on a hot day. So what you're seeing happen there is those water molecules in the atmosphere typically are intersecting a cold bottle, and it's removing energy from the system, and it's allowing those water molecules to stick together and form those droplets that we tend to think of as condensation. So we have this image here of the sun beating down on this little puddle of water and it turning into a vapor. So this is a great example of vaporization. So how would we contrast evaporation and condensation? Well, evaporation or vaporization are opposite processes. In an open air container, as what we have here with our pond on the surface of the planet, the vaporized molecules are generally going to spread out faster than they can condense. So they're going to, once they get launched, they're going to be going for it. And because there's nothing to restrain their movement, they're just going to keep going until they collide with something, which may be really, really far away from that puddle. And the net result of this is that the rate of vaporization is going to be greater than the rate of condensation, and that's going to mean that there's going to be a net loss of liquid. Now, in a closed container, such as our terrarium, the vapor is not allowed to spread out indefinitely. It's going to intersect the walls of our terrarium. And as a result, in a closed container, at some point, the rate of vaporization will be equal to the rate of condensation, because those water molecules can't go anywhere and they will intersect the wall. They'll lose energy, and they might just end up sticking together if the temperature and other conditions are just right. So what are the effects of intermolecular forces on evaporation and condensation? Well, the weaker the attractive forces between the molecules, the less energy those molecules need to vaporize. Also, the weaker forces mean that more energy is going to be needed to remove those vapor molecules before they can condense, because the trend is going to be that they're going to want to go into the gaseous state and not necessarily stay in the liquid state. The net result of this is that there will be more molecules in the vapor phase and a liquid that evaporates faster. So these weaker attractive forces are going to lead to the faster rate of evaporization. And liquids that evaporate easily are said to be volatile. Some examples of volatile liquids are gasoline and fingernail polish. And if we bring up the molecules, what we're going to see here, this is octane, and octane is nonpolar. Nonpolar molecules have fairly weak attractive forces, and it's not surprising to us that gasoline is volatile. If you set a can of gasoline open anywhere in your garage, you're going to smell it pretty quick, and that's because those molecules are being liberated from liquid state into gaseous state, and those gases are traveling throughout your garage. So you always want to keep that can of gasoline covered up, because you don't want those vapors to escape, because they're going to. And this is acetone, which is a component of fingernail polish remover, and you can see it too is doesn't have any real strong polarity to it. That doubly bonded oxygen to carbon is not going to allow for any sort of hydrogen bonding, and which means that we're looking at a fairly nonpolar molecule, which means weak forces, and it too will allow its molecules to come out of liquid and into the gaseous state really, really quickly. And if you've ever used fingernail polish remover, you know what? The minute you open that bottle, you can smell it everywhere, almost everywhere in the house. Now, liquids that do not evaporate easily are called non-volatile, and an example of this is motor oil. Now, if we look at motor oil, this is a common biodiesel fuel type molecule, and what you're going to see here is a very long hydrocarbon chain with sort of a modified carboxyl group at the end. It's not a true carboxyl group because you got this methyl group right here, which is going to create some stability with this oxygen. Now, the deal with these sorts of biodiesel fuel molecules is that this carbon chain here is typically anywhere from 17 carbons to 35 carbons long. And once you get into carbon chains that long, the dispersion forces become really, really strong, and could become strong enough that they overcome the energy that is typically available for these molecules so that these molecules cannot get launched from the surface of motor oil. So there's just not enough energy around to break up the dispersion forces that are in place in these rather long carbon chains that we see like in motor oil. Now, we have to be able to quantify vaporization in some way, because that's what we do here in chemistry. And we do that through what we call the heat of vaporization, or we might call it the enthalpy of vaporization. And when I lecture, I tend to use heat and enthalpy interchangeably. So the heat of vaporization is the amount of heat energy required to vaporize 1 mole of liquid. Now, vaporization is always going to be endothermic, as we previously established, so the value of your enthalpy of vaporization is always going to be a positive. And it shouldn't come as a surprise, this equation right down here, that the heat of condensation is always going to be the opposite of heat of vaporization, which means that the heat of condensation is going to be a negative number, because heat of vaporization is always positive, the heat of condensation is always going to be negative. Now, we defined vaporization previously as the tendency of molecules in a liquid to move to the gaseous state when it is not necessarily at boiling point. And we did look at the effects of heat on vaporization, and we said that the more energy there was in a liquid, the more likely that vaporization was going to happen. And if we look here at our chart, let's look at water. So water has a normal boiling point of 100, and the heat of vaporization at boiling point comes in at 40.7 kilojoules per mole, because remember this is a per mole. And at room temperature, it's a little bit higher at 44 kilojoules per mole. If we look at diethyl ether, its normal boiling point is considerably less than water, 34.6 degrees Celsius. And at boiling point, its heat of vaporization is 26.5 kilojoules per mole. And at room temperature is just a little bit higher. So I would say that diethyl ether is a pretty volatile liquid as a result of that. Also, acetone is pretty volatile too. Rubbing alcohol is somewhat volatile, more volatile than what we see with water. But this tells us about the energy at room temperature versus at boiling point. Now, whenever something is in a dynamic equilibrium, what's happening is that the rate at which something is getting created is equal to the rate at which something is being uncreated. And in the case of a closed container, the rates at dynamic equilibrium, the rate of vaporization and the rate of condensation are becoming equal. So the rate at which particles are leaving liquid and becoming gaseous is equal to the rate at which gaseous particles are leaving that state and becoming liquid once again. And as a result of that, there's not going to be any loss or gain in either the vapor or the liquid. Now, as we just said, when two opposite processes reach the same rate, so that there's no gain or loss of material, that's what we have with dynamic equilibrium. But what this does not mean is that it doesn't mean that there are equal amounts of vapor and liquid. What it means is that they're changing in equal amounts. So it's possible that you could have more vapor, less liquid, and that remains the same in a dynamic equilibrium situation. Now, a system that is dynamic is going to respond to changes when the conditions change. So, for example, what's going to happen is that if there is a change in the conditions, then the system will shift in order to relieve the or reduce the effects of those changes. So, for example, you had a system that was existing in a vapor liquid dynamic situation. If you were to increase the heat of that system, then you would have a shift where the new equilibrium would be reached when there's more vapor than there is liquid. If you were to take that same system and chill it, then eventually it would reach a dynamic equilibrium where there was more liquid than vapor. Now, vapor, like any sort of gas, is going to exert pressure. And the pressure exerted by vapor when it's in dynamic equilibrium is its vapor pressure. So once it's reached that equilibrium, that's what we would call the vapor pressure. Now, the weaker the attractive forces of the liquid, the more the molecules will be in the vapor. So we've already established that. So therefore, the weaker the attractive forces, the higher the vapor pressure. The higher the vapor pressure, the more volatile the liquid. And we might think about this liquid right here, gasoline, and if enough of those vapors escape, then we talk about volatility. It can look like that in a bad scenario. So what happens if you have a disruption in dynamic equilibrium because the change of volume in a container? Well, this is what's happening in a piston, more or less, and that's what we see pictured here. So keeping in mind that dynamic equilibrium gets established when vaporization and condensation are happening at the same rate. That's our dynamic equilibrium. Well, let's say that we pull our plunger out. When we do that, the volume increases, and because there's an inverse relationship between volume and pressure, when volume increases, pressure decreases. And that means that more gas is going to move into the vapor state. And in fact, it will move into the vapor state until the pressure of the system is restored. So vaporization becomes faster than the rate of condensation in those moments just after the increase of volume. Well, what happens when the opposite is true? What happens when volume decreases? Well, when that happens, then pressure is going to increase. And one of the qualities about gas is that they're compressible. And the way you compress a gas is that you can either make it smaller, or maybe you can even get the gas to condense, thereby increasing the chances of it going back into liquid. So when volume decreases and pressure increases, the rate of vaporization is going to become slower than the rate of condensation. Now we also have to talk about temperature and the effects of temperature in these systems where we have liquids moving into the gaseous state. So one of the things we could say is that when you have an increasing temperature, that's going to increase the number of molecules that are able to escape the liquid. We've established that. And that as a result of this, what we see overall is that as temperatures increase, vapor pressure will also increase. And interestingly, only small changes in temperature can actually make big changes in vapor pressure. And keeping in mind that vapor pressure is dependent upon the strength of the intermolecular forces of the liquid, we can chart how vapor pressure versus temperature looks in order to get an idea of the type of relationship there exists within our liquid. Well, what happens if we keep increasing the temperature of our system until we reach boiling point? Well, what's really happening at, quote, boiling point is that this is where vapor pressure is going to be the same as the external pressure. That's really what boiling point is. So that the amount of pressure just above the liquid is now equal to the external pressure of the atmosphere around it. And when that happens, what you're going to see is these vapor bubbles forming anywhere in the liquid, no longer just at the surface. So up until this point, all we've been talking about is a dynamic environment existing just at the surface of the liquid. Once there's enough energy into the system, then you see that dynamic environment existing throughout the liquid. That's boiling point. So there you go. Now we have to define boiling points and melting points, and in order to do that we also have to define an atmosphere. So in order for chart makers to make their charts, they have to establish a set of circumstances by which they can consider things, quote, normal. So normal boiling point is the temperature at which vapor pressure of the liquid is going to equal the standard atmospheric pressure, which is 1 atmosphere. So 1 atmosphere is pretty much what you think of as a standardized pressure whenever you're thinking of any of these gaseous systems. And atmospheric pressure does play a role in boiling point. So for example, if you were trying to boil water on Mount Everest, because there is this the pressure there is less. It's like 0.32 atmospheres instead of 1 atmosphere. The approximate boiling point of water actually reduces to about 78 degrees Celsius. If you were in Denver, Colorado, at Mile High City, where atmospheric pressure is about 80% of 1 atmosphere, then it comes in at a little bit closer to what we consider normal boiling point, which is 100 degrees Celsius. It comes in at 94 degrees Celsius. Well, if you're at sea level, which is has an atmospheric pressure of 1, then that's when we see the boiling point of water reach that expected 100 degrees Celsius. So on this slide we see a graph that's called the heating curve of liquid. There's not a whole lot of curve here. There's some straight lines. So what are these straight lines trying to tell us? Well, what we see here in our graph is that we have heat. So we have increasing heat as we move from left to right. And as we go from downward to up, we can see an increase in temperature. And here's our water basically somewhere around room temperature. And as we add heat to it, we can see that it goes up in a linear fashion, and then it starts to do something really funny right here. It stalls out. But what can we say about this linear line on our graph? Well, we could say that as you heat a liquid, its temperature is going to increase linearly until it reaches that boiling point, which at standard pressure is going to be 100 degrees Celsius for water. And we could even determine the amount of heat that went into boiling a particular mass of water with this equation right here. So we worked with this in the first part of Chemistry 1. Now, what's happening here at this flat line? What is this telling us? Well, right here is where we have our water transitioning into gas. And basically, as long as there's any water in our pot, that water can never be greater than 100 degrees Celsius, because the minute it becomes greater than 100 degrees Celsius, then it goes up. The temperature goes up again. But as long as there's water in the pot, the water temperature is going to stay 100 degrees. So once the temperature reaches the boiling point, all the added heat goes into boiling the liquid. It goes into helping that liquid do the transition from liquid to gas. And this is why the temperature stays constant. Now, once all the liquid has been turned into gas, then we get to see the temperature of the gas start to go up. But that's the temperature of the gas. So in this part of the graph, we have liquid, and then we have liquid transitioning, and now we have liquid that has transitioned to gas. So here we see the Clausius-Clapeyron equation. So what is this telling us? Well, it tells us about the dependence of temperature on pressure, because remember, we're dealing with liquids that are now turning into gases, and we know that from the ideal gas law we have taken into consideration volume, pressure, temperature, and the amount of gas that's there. But this is specifically looking to the interdependence of pressure and temperature. And when we're talking about pressure, what we're really talking about is the vapor pressure. And this dependence of temperature on vapor pressure is happening at that phase transition as the substance is going from its liquid phase into the gas phase. So if we look at the work that was done here, we can see that it says the natural logarithm of the vapor pressure versus the inverse absolute temperature is going to be a linear function. And that's what we see here. So our equation says that the slope is going to be equal to this value right here, and they put it into a formula, which is the enthalpy of the vapor over R, where R is equal to this other gas constant value, 8.314 joules per mole Kelvin. And then if they do some mathematical rearranging, they can actually calculate the enthalpy of the vapor pressure. The graph of the logarithm of the vapor pressure versus the inverse of the temperature is going to be a straight line. That's what we just set up here. And they give the slope of the line as the enthalpy of the vapor pressure over this other value of the gas constant. Now we can further expand on the Clausius-Clapeyron equation, and with 2 points, we can find the heat of the phase transition from the vapor pressures at 2 different temperatures. So it's sort of like an average, but it gives a less precise result. So basically what's happening is that you have fewer data points, and they're not going to give as precise of an average because there's less data going into that average. But still, it is a calculation that can give you an estimation. And in fact, it is used to predict the vapor pressure as long as you know the heat of the vaporization and the normal boiling point. So far up to this point, we have looked at vaporization under the circumstances of having that transaction occur in a container that is not undergoing heating or isn't constricted by the container being closed, such as what we see here with our puddle. And we've looked at what happens with vaporization when it is not subjected to heating, but it is in a closed container. And we've also looked at what happens to vaporization when we do heat it, but it's not contained. And now we're going to look at what happens when we take our container and we seal it and we put it on heat. So here we have our container with our liquid, and it's on the fire, I should say. And we're going to bring in our lid and put the lid on. And now we're going to watch it. And as we watch it, we're going to notice that the temperature increases. And that's going to force some of the molecules out of the liquid phase and into the vapor phase. And we're going to lose some of the liquid as a result of that. And if we also notice, we're going to see that the pressure went from 0.5 atmospheres to maybe 1.7 atmospheres. And then we leave it on the fire a little bit longer. The temperature increases. We're going to have more of the molecules come out of liquid, go into vapor phase, lose that amount of liquid. And we'll notice then that the pressure is also increased again. And if we heat it up one more time, we'll notice more particles coming out of solution, losing that amount of liquid, and we've had another increase in the pressure until we get to this point up here where basically all of the liquid has gone into a vapor phase, and we're at this magic pressure. Now normally if we were to increase the pressure on a gas, we would see the gas go back into a more condensed state, maybe even go back into a liquid state. But because we've added the heat, what we've done to the liquid is we have reduced the density of the liquid. We've reduced the density of the liquid until it became a gas. By not allowing the gas molecules to escape, we have increased the pressure on the gas molecules, increasing the density of gas. And what we get when we put a liquid into this sort of situation is we get something that's called a supercritical fluid. And when I say critical, I don't mean that kind of critical. So obviously in the previous example, we were able to control temperature and pressure and volume and force the liquid and gas into this odd state where both kind of existed going back and forth. Because if you compress a gas, it's going to want to go into the liquid state, but you had so much heat in there, it was forcing the liquid to go back into a gaseous state. And that's what we call a supercritical fluid. So the point at which we can create a supercritical fluid is what's called the critical point. And it involves something known as critical temperature. And this is the temperature needed to produce this fluid. So you have to get the liquid gas mixture up to a particular temperature, an excessively high temperature, in order to get to this critical temperature. You have to have a pressure called critical pressure in order for this to happen. And what's happening when you have achieved critical temperature and critical pressure is that if you were to add more pressure or higher temperatures, the gas would not be condensed into a liquid no matter how high that pressure got. You would maintain this supercritical fluid. Now the thing about a supercritical fluid is that it is man-made. mostly. I suppose there is some place deep in the bowels of the earth where we might be able to create something like this, but for the most part, supercritical fluids are things that we create in a lab. And it doesn't take much to disrupt the equilibrium that takes place in a supercritical fluid. So what we see here in this image is that we see here on the left the meniscus that exists between a liquid and the vapor that's being given off by this liquid. And as we move to the right, we can see an increasing temperature. Now we got some boiling happening. But remember, we've got a closed container. So as the temperature increases, we're also going to see an increase in pressure. And as the temperature and the pressure increase, we can see that now we have this weird uh, presence of both a condensed vapor and a less dense liquid until we reach this supercritical fluid off to the right. So as the liquid is heated in this sealed container, more vapor collects, causing the pressure to increase, and then the density of the vapor will increase, and at the same time the density of the liquid is going to decrease. And then there's going to be this magical moment, it's the temperature, critical temperature, where the meniscus is going to disappear between the liquid and the vapor, and that's when you will have achieved the supercritical fluid. And the pressure and the temperature at which those that thing happens, where you achieve supercritical fluid, that's going to be your critical temperature and your critical pressure. And the interesting thing about supercritical fluids is that they have properties of both the gas states and the liquid states. Now, when it comes to phases, changes of state, we are all familiar with something solid becoming a liquid. We would call that change of melting, and something from going from liquid to gas, and we would call that evaporation. And we go the other way, where you have a gas becomes a liquid, and that's called condensation, or a liquid becoming solid, and we would call that freezing. But it's entirely possible that we eliminate that middle state, and we have a solid that becomes a gas, or a gas that becomes a solid. If a solid becomes a gas, we call that sublimation. If a gas becomes a solid, we call that deposition. So what is happening here? Well, molecules in the solid state do have thermal energy that allows them to move around. They don't have a ton, but they do have some. And the molecules at the surface of a solid have the capacity to get enough energy to break away from the solid surface and move right into the gaseous phase. And this is sublimation. So what is an example of sublimation? Well, if you've ever left an ice tray in the freezer for long enough, and you put all the water in there, but you pull it out, and then suddenly there's like a half the tray, the cubes are filled, or maybe even less. What the heck has happened? Well, what's happened is that the molecules at the surface of that ice, with enough time, were able to find enough energy to break free and become a gas, and leaving behind less and less ice in your ice tray. So that's an example of sublimation. Now, when you capture vapor molecules into a solid, this is called deposition. So think about what's happening in the upper atmosphere on a winter day in Maine. And you have a gas up there. Most things that exist in the atmosphere are gaseous, but when the conditions are just right, that gas will spontaneously turn into snowflakes. So that is an example of deposition, where you have a gas becoming a solid. Now, the solid and the vapor that's coming off of the solid can exist in a state of dynamic equilibrium if it exists in a closed container at temperatures below melting point. So we would therefore say that molecular solids do have a vapor pressure. Now, we had a slide earlier in the presentation that looked very much like this one, except the title was the heating curve of a liquid. Here we're looking at the heating curve of a solid. And if we look at this chart, it is very similar to what we saw with the heating curve of a liquid. So what's happening here is we have our solid, it's existing, and we're getting it hotter and hotter and hotter. And once it reaches melting point, it's going to flatline because all the extra heat that is being put into our solid is being utilized to melting the solid. So that's why we see the temperature remaining the constant at this point. Once all of the solid has melted and turned to liquid, then we're going to start to see the temperature rise again until I guess it reaches possibly an evaporation point, but we're talking about things that come in at funny temperatures. I suppose that's a possibility. So for example, ice and water will always have a temperature of 0 degrees Celsius at 1 atmosphere. And as long as you have any ice in your container, the temperature is going to flatline at 0 degrees until all the ice has become water. And then it'll start to move back up. The temperature will start to increase because now we can put energy into heating up the liquid that we just formed and not necessarily having it all dumped into the solid ice we're trying to melt. Now, the energetics of melting is very similar to the energetics of vaporization. When you have a high energy molecule that leaves, the average kinetic energy of what is left gets lowered. So in this case, when you have a high energy molecule leaving the solid state, then the average kinetic energy of that solid gets lowered. And unless energy is drawn back into the solid, the temperature of the solid will decrease. And we know that doesn't happen. So we know that the solids are extracting energy from the environment or maybe some other source. So that when you have a high energy molecule leaving a solid, otherwise the solid melting, we know that this is going to be an endothermic process. It takes the input of energy to make that happen. Now the opposite of melting is freezing. This is when we go from a liquid state to a solid state, when we go from a high energy state to a low energy state. In order for that to happen, this is an exothermic reaction. We actually have to remove energy from that system to get the temperature to decrease. So then we could just conclude with saying that melting requires the input of energy to overcome the attractions among the molecules. On the next slide, we're going to be looking at these terms that you see here on the screen, and they kind of just get dropped into the lesson at this point. So I want to give you some explanation about each one of these and how you can think about them just for simplicity's sake. So when we see the heat of vaporization or the enthalpy of vaporization, I want you to think evaporating. It's the energy that goes into having something evaporate. When you see the heat of fusion or the enthalpy of fusion, think about melting, the energy that goes into making something melt. When you see the heat of sublimation or the enthalpy of sublimation, think of what it takes to make something sublimate. And when you see the heat or the enthalpy of crystallization, think in terms of freezing. So let's put these together and think about where our energy is in each one of these. So in some of these, we're going to be going from a low energy state to a high energy state. So for example, with evaporating or vaporization, we're going to be going from a liquid state into a gas state. So we're going from a low energy liquid to a relatively higher energy gas. Now, in order to make that happen, we have to put energy into the system. So we could think of energy in this case as part of the reactants. So energy has to go into the system, reactants go into the system and give us some sort of a product. When we put energy into the system, we're looking at an endothermic reaction. Now what about melting? Well, melting means we're going from a solid state, which is a very low energy state, to a relatively higher energy state, which is liquid. And in order for that to happen, we also have to put energy into this system, which means that this system is also endothermic. So it should hopefully make sense at this point that evaporating and melting are going to be endothermic reactions. Now what about sublimating? Well, sublimating is when we go from a solid to a much higher energy state called a gas. So yeah, we're going to be putting some energy into this system as well, which means it is also endothermic. Now we get to freezing, and it's something a little bit different here. In this case, we're going from a high energy state, such as liquid, to a low energy state, which is a solid. And when we do that, that means we have to take energy out of the liquid and put it onto our products side. So no longer is energy part of the reactants moving the reaction forward. It actually ends up becoming part of the products. And if it's part of the products, we could think of it becomes exothermic. And I didn't include it on here, but deposition would also be the same thing. Deposition is when we go from the gas state to the solid state, kind of the opposite of sublimation. It's also exothermic. Okay, now let's talk about the heat of fusion. So the heat of fusion is going to be the amount of energy required to melt 1 mole of a solid. And it's also called the enthalpy of fusion. So sometimes I call it the heat, sometimes I call it the enthalpy, but it's always that triangular Greek symbol with the H. And I'm talking about the heat involved with melting something, 1 mole of something. Now, melting is always endothermic, as we just showed on the previous slide, and therefore, when you see a value for the heat of fusion, it's always going to have a plus sign in front of it. So this is a situation where you don't want to leave off that plus sign. You actually want to include it when you're writing these values so that you are very intentional and expressing your understanding that if you're talking about an endothermic reaction, you know that it should be a positive. And we've already seen from previous slides that this is somewhat temperature dependent. And it shouldn't come as a surprise then that the enthalpy of crystallization is going to be equal to but opposite of the enthalpy of fusion. So the amount of energy it takes to make something go from liquid to solid should be about the same amount of energy that it takes for that very same substance to go from solid to liquid. So that's what we're saying here. So there are relationships between some of these states, typically the ones that are right next door, such as going from solid to liquid or liquid to solid. Now, what happens in a state where you actually, a transition where you're actually skipping a state, such as sublimation? Well, when we consider the enthalpy of sublimation, then we have to add to it not only the enthalpy of vaporization, but we also have to include fusion because it is going through the energetic shift in that sort of state, even though it doesn't actually go through that particular phase change. The energetics are still there in order for it to move forward, to go from a solid to a gas. It's just that it's not making a stop as a liquid along the way. But we do have to account for the energetics of it. Now, if we take a look at what's happening on the slide, we see that there is an occurrence happening here, and what's happening here is we've got ice at a negative 25 degrees Celsius, and it's going up to 0 degrees Celsius. And then we have this ice undergoing a melting, and that's what we see happening at number 2. And then number 3, our ice has melted, it has become liquid, and it is now going to come to a boiling point. That's what's happening in number 3. And in number 4, we have our water boiling, and it's transitioning from liquid into a gas. And then we have our gas phase right here. So as we look at each one of these, how can we calculate the energy that's involved? So let's go through this exercise. So let's say that we're going to heat 1 mole of ice at a negative 25 degrees Celsius up to a boiling point, a melting point of 0. So we have a couple of things here. We've got the moles, and we can figure out the mass if we really wanted to. And we've got a temperature change, and we need another piece of information. We're going to need to know the specific heat, the specific heat of ice. So let's see. We are going to use this equation where Q equals the mass times the specific heat of ice times the temperature change that the ice is going to go through. And the mass is 1 mole, which is about 18 grams. And our specific heat is right here. And if we just plug those numbers in, we can actually do the calculation. And we can see this is going to take about 0.94 kilojoules in order to make that transition happen. All right, now if we look at what's happening at number 2, we've got melting occurring. We've got 1 mole of ice melting at 0 degrees Celsius. So if we look at what we're given here, we're given a certain amount of ice, 1 mole, and we have only one temperature. So how would we account for the energy that's happening here? Well, because this is a melting and not a transition change, and we're not undergoing any sort of temperature change as well, then we're going to have to end up using the heat equation involving the the heat of fusion. So we're going to take the moles of ice, which is going to be 1 mole of ice, and now we have to look at a chart somewhere and find the heat of fusion, and that's going to be equal to 0.6.02 kilojoules per mole of ice that we're working with. So we just plug that into our formula, and we can do some math, and we can see that it takes 6.02 kilojoules of heat to melt 1 mole of ice at 0 degrees Celsius. Now we're looking at number 3, segment 3 in our heating curve, and now we're going from a, uh, a, a a temperature of 0 all the way up to a temperature of 100. So we're going to be dealing still with 1 mole of water now, and it's going to undergo a temperature change. And whenever you see that temperature change, you want to be thinking about using this formula. And now we can use a specific heat of water. We know that comes in at about 4.184 kilojoules, joules per gram Celsius, so that is a specific heat of water. And we can just plug these values into our equation, and we can figure out how much heat is needed in order to do that. And this would come in at considerably more, 7.52 kilojoules of heat needed to go from 0 degrees Celsius to boiling point for our 1 mole of water. Now, when we get into section 4, we're not going to use this equation involving mass and specific heat and temperature because we're not going to have a temperature change. So be thinking, what are we going to use here? What are we going to use here? It's probably going to be one of them things with a little triangle and an H. All right, so what's happening in segment 4? Well, we're boiling 1 mole of water in order to get it all the way up to 100 degrees Celsius. So here we're going to be using Q is equal to the amount of water that we have, the moles of water, times the enthalpy or the heat of vaporization. And we know that our moles, we have 1 mole of water, that's how many moles we have, and we're going to look on a chart somewhere and find the heat of vaporization, and we'll plug it into our equation, and we'll do the calculation. And here we are in segment 5 of the heating curve of water, and we're looking at the creation of steam. So what are we talking about here? Well, we're talking about heating 1 mole of steam at 100 degrees Celsius all the way up to 125 degrees Celsius. So if we're seeing this temperature differential, then we're thinking about using this equation, and we have to have the specific heat for steam, which we would find on a chart. There it is right there. And we just plug in the numbers, do the calculation, and we find that value as well. So this is kind of putting all of those values together and how you could calculate the energy demands of water or some other substance as it goes through its heating curve. Or actually, even as it's going through its cooling curve. It'd be just the opposite. So phase diagrams are kind of fun because they have on one picture all the dynamics of what's happening for a substance between all the possible states. So what we see here is along the bottom we have the temperature, and then along the side we have the pressure, and we know that there's a relationship between temperature and pressure, and that you can alter those and you can make a substance go into different phases. And we see here we have the state of solid and liquid and gas. And then we have this line here. This is the sublimation curve. So this is that transition that would take place between something going from a solid to a gas. Or I suppose you could go from a gas to a solid. And then on the other side of the fusion or the melting curve right here, we would have the vaporization. So that's what's happening between liquid and gas. So here it is all together. And then out here at the end you have the creation of your supercritical fluid. So this critical point tells us about the creation of that. So if you had information, say like you had 1 atmosphere, you were at 1 atmosphere, and you had a substance that was coming in at about 50 degrees Celsius, which is actually pretty hot, then water, in the case of water, you would actually still have water at 50 degrees Celsius. But what if you came in, oh, I don't know, let's just say maybe this is like 5 degrees Celsius and you were coming in at maybe 690 torr, clearly not 1 atmosphere. Well, then you'd reach this magical thing right here called the triple point. And the triple point, I'm going to point it out down here, the triple point is the temperature and pressure conditions needed in which you would have all three states of a substance existing simultaneously. So at a triple point, this is like this magical moment where you would have some of the water in solid state, some in liquid, and some in the gaseous state. Just like at the supercritical fluid point, at the critical point, you would have water existing both as a liquid and as a gas. So it's kind of neat to look at and daydream about the conditions necessary to make water do different things. So here's a phase diagram for a different substance. I don't think we really need to know what it is because we're just going to talk a little bit about how to move around and see what it is that we're talking about. So let's say that we had a substance that was coming in at, oh, I'm going to come down here roughly 25 degrees Celsius. If we had something coming in here, negative 25 degrees Celsius, we could come up here and we knew it was at 1 atmosphere. Boop-a-doop. We could pretty much see that that's going to be existing as a solid because it's falling within the area of the solid phase. But what if we had something coming in at 0.006 atmospheres? And we were at solid. Well, we could pretty much guess then that a temperature is probably going to be somewhere less than 0.01 degrees Celsius because at 0.1 degrees Celsius and at this particular pressure, we're going to end up with at the triple point. That's probably why that's pointed out there. So yeah, if we were, say, negative 25 when we were at this, we would know that we're going to be at a, we're still going to be in a solid. But what if we came in at 25 degrees Celsius and at 0.006 atmospheres? Well, then we're going to be at a gas. And what if we were at 25 degrees Celsius and we were at 1 atmosphere? Well, then we're going to be at a liquid. So this is how you would kind of navigate around using a phase diagram. So what we see here is our triple point where we have the existence of all three phases right here, solid, liquid, and gas at that magical point right there. We have the fusion curve, which says that at particular pressures and particular temperatures, this is the way that melting is going to happen. So you could actually have, let's say that we were just a little bit beyond maybe 0.02 degrees Celsius right here, then we would be just beyond the triple point. Oh, and we're going to be at this particular pressure, Then we would be just a little bit beyond that, and we would maybe be in the gaseous state. But what if we were just maybe a little bit higher temperature still, or a little bit higher pressure still, then we'd be in the liquid state. So this is, I think you guys get the idea of how to navigate one of these. Let's take a look at a couple of substances and look at their charts side by side. Okay, so here we have iodine and carbon dioxide. Now the temperatures are not to scale, and neither are the pressures. And if we look, here's 100 atmospheres, here's about 73 atmospheres, we're down to 1 atmosphere, we're down to 1 atmosphere. That is kind of, those are coming in together. But the temperatures are clearly not, because here we have a negative 78 Celsius and here we have 114. But you still get the idea, just looking at these two, that they're going to behave very differently at different pressures and at different temperatures, and you can negotiate each one. So I could say, can you tell me about what's happening at, oh, I don't know, maybe, let's look at this, at maybe 50 degrees Celsius for each one of these and 1 atmosphere? Well, we have to do some guessing. So let's say we're here 1 atmosphere all the way. Well, we're going to be at a gas here in carbon dioxide, because we can see at 31 and 1 atmosphere we're going to be at gas. And so if our temperature continues to go up, we're going to still be at a gas. But over here we're at 114 and we're at 1 atmosphere. Oh, something very different is happening with iodine. We're going to be at a solid with iodine. So at about 50 degrees and 1 atmosphere, we're going to be at a solid. So, That's just kind of doing a comparison and contrasting and seeing how different things behave differently. So here's the triple point for iodine, comes in at 114 degrees at 1 atmosphere. Triple point for carbon dioxide comes in at 5 atmospheres. Wow! And a negative 56 degrees Celsius. Very different. So there that is. Now, unless you watch this all the way to the end, you're not going to learn this because this is it. In section 11.9, water and extraordinary substance, we're actually going to hold off on this and move it to what I call the hodgepodge chapter, or the hodgepodge selective selections. And I'll tell you the reason why I had to do that is because in order to make to cover all the bases in the second chemistry, my choices were to include 2 additional chapters, which were very information dense, or just pull out certain selections and create a focused chapter to ensure that I covered everything. And so that's what I've chosen to do. So, and that's what I've done. And so what that means that section 11.9 is not going to be covered on the exam. We're going to actually move it into the next exam, and you can call it quits for chapter 9 once you get to here. And with that, we are done.